We will be looking at question 18, October 21 paper. This question is about redox titration and redox reactions. Let's have a look. A student carries out an experiment to determine the percentage by mass of copper in an copper ore containing copper in its 2+ oxidation number. The student is provided with a sample of copper ore, 1 mole per decimeter cubed of potassium iodide, and you've got this concentration of sodium thiosulfate. You see, why did I not highlight the potassium iodide? Because this is going to be in excess. If you compare this concentration to this, the potassium iodide is far, far in excess, even though we're using a lower volume. It tells you in the question here as well, excess. So we don't really need to worry about that. The student's method is below. You've got this mass of the ore. The copper-2 compound in the ore reacts, forming aqueous 2+ copper nitrate, copper-2 nitrate. Filter the mixture to remove the unreacted rock, neutralize the filtrate. Add excess potassium iodide, A precipitate of copper-1 iodide and a solution of iodine is formed. And you see, because this iodine is formed here, that iodine is then titrated with thiosulfate ions. And we've got here this volume and this concentration of thiosulfate were required to reach the endpoint. So we've got all our main bits of information we need there. Suggest the formula of copper-2 compound which reacted with nitric acid to form the gas, and write a full equation. Where did it form a gas? Or to form the gas. Okay. Oh, the student observed that bubbles of gas were produced. If it's a copper compound and it's going to form a gas, the only type of compound of a transition metal you could have is a carbonate. So we're very likely to be dealing only with a carbonate. There could be other options. Could there be a sulfate? There could be a sulfate, but we've not learned those reactions in our specification. So the carbonate is the main one. So what we've got here, we've got copper to carbonate. This is a year 1 type of question where you've got a carbonate reacting with an acid to give you the salt, water, and carbon dioxide. That's the gas that's given off. And to balance, just put a big 2 there. Write an ionic equation for the reaction in step 3. In this question, they give you quite a bit of information about this equation, but otherwise you do need to learn it off by heart. It does come up. And that's when you've got copper 2+ ions reacting with iodide ions. And this gives you copper-1 iodide, which it tells us in the question. And also some iodine is given off. And to balance, we put the iodide ion, copper is going to gain 1 electron, iodine is going to lose 1 electron. So you've got the oxidation numbers there. So that's really and then you've got your extra iodide ions. So we're going to put 2 there, a 4 there, and a 2 there. The mark scheme, yep, supports that. And I'm just double checking. And the reason why I was referring to the oxidation numbers, you can check, you got +2 oxidation number here, -1 here. We've got +1 here. That's still -1, but this is now 0. So remember, in these instances, the electrons have to balance as well. Suggest a suitable indicator for this titration. State the color change. You see, when you've got iodine in step 4 is the titration. And so the indicator that we use is going to be starch solution. And what does the starch solution go to? It goes from a blue or a very dark blue, what does the masking allow? Yeah, it allows for blue. It's actually they're referring to it as a blue-black solution, but blue is acceptable, dark blue, and it goes to colorless. If you've done this experiment, it gives you a very the end point is very easy to determine, unlike other indicators in acid-base titrations. It's then asking us determine the percentage by mass of the copper ore. Give your answer to an appropriate number of significant figures. Let's have a look. So here, we've got our volume and concentration. So we've got here 26.55 26.55 divided by 1,000 multiplied by, what's the concentration? 0.02 equals, now this is of the S2, the thiosulfate solution. Let's work this out. This gives you 5.31 times 10 to the -4 moles. You see, if you look at the ratio between the thiosulfate ion, which is it's a 2-to-1 ratio. How do you make 2 into 1? Oops. How do you make 2 into 1? You divide that by 2. So how much iodine will there be? 5.31 times 10 to the -4 over 2. This gives you 2.655 times 10 to the -4 moles. Now you see, the iodine, this is the iodine that was produced from this is the iodine that was produced from the copper in the copper ore. So this actually is a 2-to-1 ratio. How do you make 1 from the iodine into a 2 copper? You multiply it by 2. So look, we actually multiply it back to 2. 2.655 times 10 to the -4 multiplied by 2 gives you the same answer. And now that we know how much moles of copper we have, we multiply that by copper's relative atomic mass. Copper's relative atomic mass. What's this? Copper is 63.5, so 5.31 moles of copper times the relative atomic mass of copper. That gives you 0.0337185 grams. And to work out the percentage by mass, this is the mass of copper, pure copper, and the total mass of the ore was 2.50 grams. So 0.0337185 divided by 2.50 grams multiplied by 100, and the appropriate significant figures, usually it's 3. You'll use the smallest significant figures they've given us. Well, 3 is the standard, really. .34874, and the percentage in 3 sig figs will be 1.35%. Let's have a look at the mark scheme. Yep, 1.35%. Where are the marks from? Volume times concentration, 1 mark. The ratio conversion, any one of these, 1 mark. Multiply the moles by the relative atomic mass of copper, 1 mark, and the percentage, 4 marks. Some questions about the procedure. It's asking, explain whether the calculated percentage by mass of copper would be higher, lower, or same. So the percentage of copper would be higher, lower, or the same if potassium iodide was not in excess. If potassium iodide was not in excess, if this was not in excess, that means there's going to be less iodine forming. If there's less iodine forming, that means in the titration, you're going to be using less thiosulfate solution, which in turn will give you a smaller titer. And so if it's a smaller titer, then it's eventually, so if this value is smaller, that's going to be smaller, that will be smaller. It's all going to give you a smaller percentage by mass. Smaller percentage by mass. And why is that? Because less iodine produced. Or you could say sorry, they asked us to use the word lower. Lower percentage by mass, and this will give you a smaller titer. Next question is asking about, you see, this is your burette, and if this is your initial reading, and this is your final reading, usually whenever you read off the meniscus, it's supposed to, you read off at the bottom of the meniscus. Yep. But if you're reading incorrectly, but you're reading at the top of the meniscus, you see, if the burette's reading from the top, will it make any difference to the percentage by mass? No difference. The percentage by mass will be the same. Why is that? Because the burette readings are used to calculate the difference. If it's only one burette reading, then that will affect. But because we're looking at the difference, that is going to be the same as that. So it really wouldn't make a difference. Okay? The student then modifies the method in order to obtain a more accurate value, a more accurate value for the percentage by mass of copper in the ore. The student decides to use a 10 times greater mass of copper ore. What further modifications should the student make to produce more accurate value for the percentage by mass. If you look at the titration procedure, there's quite a few things you could do. Now, one way of looking at it is you see the percent, anything that can reduce this makes it more accurate. How is the percentage error calculated? It's usually maximum error or measurement error divided by the measured value. Actually, let's call this measurement error. And times by 100. So for example, we used a 2 decimal place weighing scale. Let's use a 3 decimal place weighing scale. So this could be one. Use 3 DP weighing scale. And how would that make a difference? You see, going from 0.005 plus or minus, you're going to plus or minus 0 point minus 1. That's 3 decimal places, and it's rounded up or down from the 4th. So you're reducing this. Yep. That in turn will reduce the percentage error. So you use a 3 decimal place weighing scale. This is worth 2 marks. So we need to give another point. What else could we do? You see, only 1 titration was done. Usually questions like this should be made up to a standard solution, like 250 centimeters cubed. Yep. And from that standard solution, we can repeat titration to achieve consistent, or the term we're looking for, concordant results. Concordant results are usually in the 0.10, close to. Yep, I think that's the end of that question. See you tomorrow.